Hey folks, welcome back to another lesson, and we're going to move on to a new topic which is called irradiance. And we're going to define the irradiance, describe the inverse square law, and explain how to use the relationship between irradiance and distance. Okay, so to start off with some basic background information. So a light source will give out light or photons, as you'll see later on, and light always travels in a straight line. So just like field lines are always straight lines, light always travels in a straight line. And this is where it's a wee bit weird, but when the light hits an object, it can either bounce off in a new direction or it can be absorbed. Now, the light that is bounced off in a new direction, it can go into your eye or into a camera, and that is the light that gives the color of the object. So it's a bit weird. Whatever wavelengths of light that are absorbed by the object means that you don't get to see it. So the only thing the color of an object depends on is actually the light that it reflects off. So one of the questions we're going to try and answer in this lesson is, why is a laser more dangerous than a light bulb? And you've probably heard stories about how firemen or pilots have a laser shone in their eyes when they're trying to drive a vehicle, and then that can be quite dangerous because the laser can make them go blind and they can cause accidents. So why is that? And why is it that you can shine a light bulb without really blinding somebody? So let's get to some definitions. So we're going to start with irradiance, which is defined as power per unit area. So I'd like you to write this down, okay? Now the irradiance could be the amount of power hitting in a certain area, or it could be the other way around, where it's a certain area giving out a certain amount of power. So the equation for irradiance is given by power over area, or P over A. Irradiance is in watts per meter squared. So here we have there. Power is in watts and area is in meters squared. Now make sure you are familiar with this equation and you can find it in your relationship sheet. So going back to our earlier starter question, lasers have a high irradiance whereas a bulb has a low irradiance. Why is that, and how does that make lasers more dangerous than a bulb? Well, it comes back to this equation here, and in particular the area. Because if you think about a laser is usually a very, very narrow beam. So that means the area that the power is spread over is very small. So that means it has a very high irradiance. At the same time, if you think of a bulb, it has a very large surface area. So that means the power is spread over a bigger area. So that's why its irradiance is a lot smaller. That's also the same reasons why a laser is more dangerous. Because the power is more concentrated, it means you're going to get more power, more energy per second than if it was spread out. And so this is why lasers are really dangerous and you should never point them at your eyes. Whereas with a bulb, you can look at it without really damaging your eyes in the same way as a laser would. Okay, so let's look at the experiment that you're expected to know. And of course, if we were in class, we could do this experiment, but we'll just talk about it just now. So the idea is fairly simple. We're trying to find the relationship between irradiance and distance. So we have a light sensor, which measures the irradiance. We have a meter sticks, which measures the distance of the light sensor from our source of light. Now, this source of light is called a point source. So I'd like you to copy this down along with the diagram so you know what the experiment is. And it's that point source is an ideal source of light in which all the light comes from a single point and is evenly distributed. So make sure you know this definition. And why do we need to know that? Because one of the most common exam questions you'll get about this experiment is, why do we use a small bulb instead of a big bulb? Okay, and the answer is this. Well, first of all, if it's a small bulb, you can see the surface area is fairly small, so that means the light is going to get spread out in a pretty kind of even manner. Because the area is small, you're not going to get a lot of variation. The light's going to be given out fairly evenly. In contrast, if you've got a big bulb, okay, you could imagine that the light coming out, some of it might hit the bottom bit like this, rather than going forwards towards the light sensor. So this is why you use a small bulb, because it's like a point source. And a point source is an ideal source of light in which all the light comes from a single point and is evenly distributed. So it's really this idea that it's evenly distributed. So make sure you know that explanation as well. Okay, so this is the actual equipment you would be using. We'd be using Alba. You can see you've got the data logger, the light sensor, and our point source here. And then this sits on a ruler, so we can move it away and know what the distance is. So what I've done, folks, is I've generated some data, and you can see we've got the distance there in meters and the radiance in watts per meter squared. And the first thing we do, as always, is we plot a graph of I against D. And this is the graph that we get. I've done it on Excel. We've got I along the y-axis and D along the x-axis. Now, this isn't our kind of usual proportional relationship, but you may remember this from the gas laws in Nat 5, where we got a curved graph, and the next thing we did to get the relationship was to do the following. We plot a graph of I against 1 over D squared. So feel free to work out D squared, and you can leave this blank just now, and then we plot the graph. So here we have I along the y-axis, and 1 over D squared along the x-axis. And what I hope you will find is that we get a lovely straight line through the origin, so there is definitely a relationship there. But it's not proportional. Because we had to do this twice, hopefully you remember we call it an inversely proportional relationship. So here's how we write that down. So if you can write this in your jotter, I is inversely proportional to D squared. Okay? And we can rearrange this to write this as K is equal to I times D squared. So this means irradiance and distance squared are inversely proportional. Now it's inversely because you've got a 1 over D squared, and this K here is just a constant that always appears when we do this. Now this form of the equation is the one that's more useful to us because it's got an equal signs, which means we can calculate things. Okay, so inverse square law, as I said at the start, you've come across an inverse square law before, which is this one here. F is equal to GMM over R squared. Because if you think about it, this really here is a constant, so I could write this equation as K over R squared. Okay, and we could do the same trick here, because we could really write this as I is equal to K over D squared, so they've both got the same form. So it's called an inverse square law because you're taking the inverse of the square of something. Okay, now another common exam question they might ask you is, use this data to show the relationship between I and D without drawing a graph. Okay, so how do we show that I is inversely proportional to D without drawing a graph? So let's look at the method for this on the next slide. So first of all, we've got our two sets of data here, and the trick is we want to use this equation to show the relationship. So what we try to do is we want to square D, multiply it by I, and we should get a constant every time. So let's see if we get that. So first of all, I square D, so feel free to check that that's correct. I then multiply each value of D squared by its corresponding value of I. So what I'm doing is I'm doing this basically. Okay, 20 times 0.01, 5 times 0.04, 2.2 times 0.09, so on and so forth. And you can see for each kind of multiplication, I get the same value each time. So what I've done is I've shown that this relationship is actually true. So therefore, I must be inversely proportional to D squared. Now, how might you get caught out by this? Well, sometimes when you do the multiplication here, you might not get exactly the same value. So you might get something like 0.19, 0.21, or 0.18 even. Okay? In that case, because it is experimental data, you wouldn't expect it to always be the same. So as long as you can round it up to give you roughly the same answer, then that's acceptable. So just to summarize all of that, we multiply each I by D squared. Since we get a constant each time, this shows that irradiance and distance squared are inversely proportional. So make sure you know how to do that technique. If you want, you could even copy down this and this as well. And finally, K equal to ID isn't really that much useful. So this is the actual equation you're going to be using in the next lesson. So just to give you what this equation is, it means the radiance at point 1 times the distance squared at point 1 is equal to at some other irradiance at another point times the distance at that other point squared. And we're going to see how this equation is used in some worked examples in the next lesson. So just to summarise, folks, you need to know the definitions of irradiance. You need to know the experimental technique and the use of a point source. You have to be able to analyse the data, so in terms of the graphs and relationships, and you have to be able to show the relationship without drawing a graph.